Right now, your phone is doing this. A handful of satellites, each one swearing you're a certain distance away. And they disagree. Draw a circle for each, and no single point sits on all of them at once. So your phone doesn't find where you truly are. It finds the place that's least wrong, the spot that misses every satellite by as little as possible. Squared. Where are you, really? This is least squares. That was least squares in the wild. Noisy, curved, groping its way to an answer. Now watch it in a straight world, where it becomes something beautiful. Picture a field. Your friend is standing out in the grass. That's your data, where the truth actually landed. You can only walk on a path. Widen that path into a flat, open clearing. And the clearing is everything your model can produce. Every knob you can turn is one more direction you're free to walk. You will never reach your friend. The only question is where to stand. How wrong are we? Measure the gap from the clearing up to your friend, for every point, and add them all up. But not the gaps themselves. They're squares. On screen, the data is y. The model's reach is x beta. Each gap between them is a residual, r. And the number we drive down is the sum of the squared residuals. Why the square, and not the gap itself? Hold that thought. It's a choice, and we'll come back to it. Now, the sun. Straight overhead. Noon. Your friend, out in the grass, casts a shadow, and it falls right onto the clearing. Look where that shadow lands. Of every spot on the whole clearing, that one is the closest you can possibly get to your friend. The shadow is the answer. Let's give it a name. Where do you stand? Right at the foot of that shadow. We call it the fitted values, y-hat, the projection of your friend onto the clearing. But why there and nowhere else? Watch the gap. At the foot of the shadow, it points straight out, a perfect right angle to the clearing, to every direction you could have walked. The model has taken everything it can reach. What's left has nothing in common with it. X transpose R equals 0. Step anywhere else on the clearing, and the gap only grows. A slanted line is always the hypotenuse. So, where exactly? Write that right angle condition down in the clearing's own coordinates, and it becomes a small system. The normal equations. Solve them once, and out comes beta hat, the pseudo-inverse of x times y. No searching, no wandering, an exact address. Remember your phone, groping toward its position. Its circles were curved, so there was no exact answer. It had to feel its way there. Straight in the world, and the whole problem becomes one smooth bowl. We jump straight to its floor, and the entire shadow is a single machine. The hat matrix, H, casts the shadow twice, and nothing moves. A shadow is already flat. But how did we measure far? Let your friend wander off, way into the distance. There's more than one way to say how far away they are. Straight across, as the crow flies, or block by block, like a taxi through city streets. 2 rulers, and the ruler you pick is about to decide the entire fit. Who chose squared? You did, the moment you said distance. Straight line distance gives you least squares. The L2 fit, the one that lands on the average. But switch to the taxicab ruler, which doesn't care how far, only that you missed. And you get L1, least absolute deviations, the fit that lands on the median. Now watch what happens when one point runs far away. Under least squares, it's square balloons, and the whole line swings out to chase it. Under L1, the line barely flinches. Squaring means you fear the far miss. And one outlier can bend everything. What if some of your measurements are shakier than others? Then trust them less. Weight each point by its reliability, one divided by its variance. The points measured in fog count for little. The clear ones pull the hardest. It's the same shadow, just cast onto a tilted floor, where straight down now means something new. Pharmacometricians know this one well. It's the weighting inside every proportional error model. Can a perfect fit still fool you? It can. Suppose two of the directions you can walk are nearly the same, and the clearing folds into a crease. Your standing spot, Y hat, is still pinned down perfectly. But how many steps you took along each near-identical direction? The coefficients, beta hat, can swing wildly, flip sign, blow up. The fit looks flawless. The numbers underneath are noise. The condition number, kappa, screams. And the cure is a gentle leash. Ridge regression, pulling the coefficients back to something stable. If you saw the last to settle, you've met this ghost before. So is the shadow the truth? Here the picture points past itself. If your friend really did start on the clearing and drifted off by pure random noise equally likely in every direction, the round, Gaussian kind, then the foot of the shadow is the most likely place they started. Least squares is maximum likelihood, the very heart of a tailor with no taste. And among all the fair, unbiased ways to average your data, it is the best there is. That's the Gauss-Markov theorem. But the shadow is only ever as good as the clearing. If the truth was never on it, the leftover isn't noise. It's bias, an error no amount of data will ever remove. Least squares gives you the best answer your model can give. Not the same thing as the right answer. Let's bring the threads together. Your friend was the data. The clearing, everything your model could produce. The shadow, Y hat, the closest it could get. The gap, pointing straight out at a right angle. The ruler you chose. The fog that reweighted your trust. The crease that scrambled your coefficients. And the overhead sun. The Gaussian noise that made the shadow the likeliest answer of all. That phone at the very start, it was doing exactly this. Just badly, because its circles were curved. The same shadow fits every drug's concentration curve and lives inside every linear layer of a neural network. You never really reach the data. You reach its shadow, the closest thing your model is allowed to become. And the error, it always points straight home. The best fit is a shadow, and the error always points straight home. But here's a last thought. What if the satellites themselves were in the wrong place? What if the very directions you walked were measured with error too? That's a different shadow. That's a story for another day.